Heisenberg's uncertainty principle. Okay, so Heisenberg's uncertainty principle is one of the core concepts when it comes to quantum mechanics and also in terms of just how our world works in general. But the results of this principle are pretty, counterintuitive for a normal person who doesn't have any background when it comes to quantum mechanics, which also means that I was extremely confused when I was going through this, but hopefully this can help make it a bit clearer for anyone watching this. So, at its core, what is Heisenberg's uncertainty principle? What is it talking about? And how do we know that it exists, right? This is what we're going to try and answer in this video. So, at its core, Heisenberg's uncertainty principle talks about two things. It talks about position and it talks about velocity. Okay. And now what it says, this is the counterintuitive part. What it says is that position and velocity for any given object is not, they are not defined quantities. They do not exist as a definite value. You can never exactly define the position or velocity of an object. Now, like I said, this is the part that seems like it doesn't make any sense. Because let's take the example of a cricket ball, right? Let's say a bowler is bowling, and he has a cricket ball. Now if he's holding the ball in his hand, he knows where the ball is, right? If you asked him, he would say that he knows exactly where the ball is. And if he bowled a ball to the batsman, and you have your speedometers and everything else, you would say that you have a pretty good idea of how fast the ball is moving. But that is where the paradox of this principle lies. It says that you can never really define the position or a velocity or the velocity of an object exactly. And it also says that the uncertainty in those two quantities are correlated, meaning the more you know about the position of an object, the more certain you are of its position, the less certain you are of its velocity, and vice versa. If you are more certain of its velocity, then you are less certain about its position. So that's what the principle at its core says. Now, how do we know this exists, right? Where can we see this? Because, like I just said, in our daily life, we don't really see evidence of this principle. And we'll get to why that is in a little bit. One very famous example for demonstrating this principle is the Young's double slit and Young's single slit experiment. So let me just try and show this to you. Okay. So let's say you have a slit like so, and then you have a screen here, and then you're shooting particles through this slit. Okay. Forgive my rough drawing skills, but okay, that should be, should give you an idea. Now, if you're shooting the particles through this slit here, by common sense, you would expect them all to line up roughly around this area. Maybe some of them hit the edge of the slit over here and they go off towards the side, but roughly you would expect all of them to show up here, right? Now, what we can do here is actually reduce the size of this slit, all right? Now, if you reduce the size of this slit like so, you are reducing the amount of space the particles have. Now, initially what you would expect is that all the particles would be falling in a more concentrated area because there's less space for the particles to move through here, right? So you'd expect them to be more clustered like so. And initially this is what happens, until this point, everything seems like, it's working fine. We understand what's going on. Everything's working perfectly fine. What is a little bit more interesting is what happens when you reduce the size of this slit even further, when it's like even smaller, right? Now, if you actually do this with like a laser or something like that, you'll actually see that instead of getting even more concentrated, this light that you see on the screen here starts to get more spread out, which doesn't make any sense, right? Because you have a smaller position. But this is exactly what Heisenberg's uncertainty principle says if you think about it. So what we're actually doing here, by reducing the size of this slit, you are actually reducing the uncertainty in position, right? You're giving it a smaller position. So smaller position would, by common sense, it would mean smaller uncertainty. But as Heisenberg's uncertainty says, the or the better you know the position of a particular object, the less you know about its velocity or its momentum. So that's what happens here. So as the position's uncertainty decreases, the uncertainty in its momentum increases. So then it's just kind of a random roll of the die, if I can put it that way. So then, because the momentum is random, it gets spread out over the screen instead of being focused into a even tighter cluster. So this is one example that I can give you of how we know that this principle exists and how this is, um, you know, a proven phenomenon, even if we don't fully understand it. At least I don't fully understand it. Maybe there's someone else who fully understands it. But we also have a mathematical expression for this. We have this formula here: delta x times delta px is greater than or equal to h by 4 pi. Now, just to go over the quantities here, you have h, which is just your Planck's constant. If you are familiar with the Planck's law, energy being quantized, E is equal to h nu. And then you have delta px here. This is your uncertainty in terms of momentum. And in this particular case, since we're only talking about the x-axis, this is the x component of momentum. Okay, so we're only considering 2D examples, which is why we don't have to deal with other components. But yeah. And finally, we have delta x, which is again uncertainty in position. All right. So now we have a mathematical expression. We have an inequality which says that the uncertainty in the position times the uncertainty in momentum is always greater than or equal to h by 4 pi. Just a little note here, h by 4 pi, let's write this here, is also written as h cross by 2, where h cross is equal to h by 2 pi. This is just a notation that is used, so it's just something to keep in mind. So you have this mathematical inequality with which you can talk about how, to a certain degree, you can talk about the magnitude of the uncertainty in terms of position or in terms of momentum. Now, you can also rewrite Heisenberg's uncertainty principle in a few other ways. You can also write it as delta E times delta T is greater than equal to h cross by 2, or delta L times delta theta is greater than equal to h cross by 2. It's essentially just the same principle, just written in terms of slightly different quantities. So delta E refers to uncertainty in the energy of a particular state. Right, energy of state. And delta T is the uncertainty in the lifetime of that particular state, or how long that particular state can exist in a stable condition. Lifetime of state. There we go. And delta L and delta theta are actually even more similar to the first two quantities, where delta L is uncertainty in angular momentum. And delta theta is uncertainty in angular position. All right, so now we've got ourselves, we've got ourselves a mathematical equation We've got different forms of that equation for different quantities. That's great. But in the beginning, we were talking about how this is a fundamental principle and how this is how the world works, but we don't really see that in real life. And why is that? Well, this is again something that is, a characteristic of quantum mechanics in general. When you go down to really small sizes, the behavior of particles and atoms and everything else is very peculiar when compared to the behavior of what we consider as normal objects or objects that we can see around us in real life. So let's actually just take an example and apply Heisenberg's principle and just show you why you can't actually see this principle in any noticeable way in real life. Okay, so let's go back to our previous example. Let's talk about a cricket ball. Okay, so let's say that the bowler has balled a ball and it's going at some speed. All right. So let's see if we can calculate the momentum for this ball. All right. So we know that P is equal to m into v. So the mass of a cricket ball is 160 grams, which is 0.16 kgs, and the velocity would be, let's say it's a fast bowler who's bowling like above 140 kilometers per hour, which would be like approximately 39 meter per second. Of course, I'm not doing this in my head. I have this written down here. Yeah, so when you multiply this, you get 6.24 kg meter per second. Okay, so this is the momentum of our hypothetical cricket ball, right? Now let's say that we are not 100% certain. There's like some error in our measurements, but you're reasonably certain. Okay, so let's say there's only like a 1% uncertainty in the momentum. Okay, so that would mean that delta p is 1 by 100 times p, which would be 0.0624 kg meter per second. All right. And now we have our Heisenberg's equation, right? So we have delta x times delta p is greater than equal to h by 4 pi. And we're just trying, so it's greater than or equal to h by 4 pi. Let's just try and get a lower bound for delta x. Okay, so let's just consider it to be equal. And in that case, we would get the expression to be delta x equal to h by 4 pi delta p. So substituting the values here, you would get delta x to be 8.45 into 10 to the power minus 34 meters. Now here, this gives you a clear idea of why you can't see the Heisenberg's principle in action in real life, right? Because this value, as you can see, is extremely small, right? 10 to the power minus 34 meters. The smallest shift that we can possibly notice in real life is maybe what, a millimeter shift, if that, and that's if we're looking for it. 10 to the power minus 34, if there's a shift in position by even 1 into 10 to the power 30 minus 34 meters, you're definitely not going to notice it. So this just goes to show you that the uncertainty principle is not something that is restricted to quantum mechanics necessarily. It is definitely a universal principle that applies to all objects. But the only problem with that being that for most macroscopic objects, or the objects that we can see around us in real life, uh, the sizes and the magnitude of the quantities are so high that the uncertainty really doesn't make any difference. But when we are dealing with atoms and particles at such a small scale, where the average size of an atom is something like, uh, I think, 10 to the power minus 10 meters, then you can see how the uncertainty would start to play a major difference. And again, if you're considering an atom, just to, I guess, show you here, if you had an atom like so, the majority of the mass of the atom would be contained in the nucleus. So if for example, this is a nice example. If for example, the room you're sitting in right now, was the size of an atom, right? Then the nucleus would be the size of a grain of sand, right? But that one grain of sand would contain like 99% of the mass of the atom. So if you're talking about the nucleus, then you're talking about an even smaller scale. So at such small scales, that's when these uncertainties really start to pan out, and there's a major difference when you take those uncertainties into account, which is why you have a lot of probabilities in quantum mechanics, and why Heisenberg's uncertainty principle is so fundamental when it comes to dealing with quantum interactions between particles. So, yeah, that was it about Heisenberg's uncertainty principle. um, I'm not sure if I'll keep doing this kind of thing, but if you did find this useful, then I'll see if I can make this a regular thing. Yeah,